Orthonormal basis, Gram-Schmidt process. Orthogonal and orthonormal sets. We worked quite a bit recently with orthogonal vectors, or vectors that were at a 90-degree angle or perpendicular. Now we want to take a look at an entire set of vectors, and when every pair of vectors in S is orthogonal, then the set is called orthogonal. And if in addition each vector in the set is a unit vector, then S is orthonormal. So let's just verify a few of these before we talk about why that's important. So here we have three vectors, v1, v2, v3. The first thing I'm going to do is verify that this is an orthogonal set of vectors, meaning I have to take a look at v1, v2, v1, v3, v2, v3. And we're just going to determine if they're orthogonal. Now, if you'll notice, it's an inner product space, but we're not given a definition for that space, so we're going to use the dot product. So it will either be defined for you or you'll use the dot product. So here for v1, v2, that means 1 times 0 plus 0 times 1 plus 0 times 0, which is 0. For v1, v3, we have 1 times 0, 0 times 0, 0 times 1. And then for v2, v3, 0 times 0 is 0, 1 times 0 is 0, and 0 times 1 is 0, and that's 0. So what I have determined is that S is an orthogonal set. Now, I need to determine that it's an orthonormal set. So an orthonormal set is where we have an orthogonal set and each vector is a unit vector. So in order to determine that, I'm simply going to find the length of v1. And if the length is 1, then it's a unit vector. So the length of v1 would be the square root of 1 squared plus 0 squared plus 0 squared, or the square root of 1, which is 1. Let's do the same for v2. So for v2, I have 0 squared plus 1 squared plus 0 squared. That's the square root of 1, or 1. And then for v3, I have the square root of 0 squared plus 0 squared plus 1 squared, which is the square root of 1, which is 1. So by determining that each pair of vectors is orthogonal, we have an orthogonal set, and now I can say S is an orthonormal set. Because in addition to having an orthogonal set, each of these is a unit vector or has been normalized. Let's do the same for a slightly more complicated set. We have S is radical 2 over 2, radical 2 over 2, 0, and then radical 2 over negative radical 2 over 6, radical 2 over 6, 2 radical 2 over 3, and 2/3, negative 2/3, 1/3. We're going to perform the exact same steps. First, determine that each pair of vectors is orthogonal, and then determine if each vector is a unit vector, therefore it is an orthonormal basis. So I would like you to try this question on your own. Press pause. When you're done, press play to see how you did. So the first thing we do is that we have to show this is orthogonal. And orthogonal means when I take each pair of vectors, I end up with 0 as the dot product. And again, we're just given a normal dot product here. So I do get 0 and 0 and 0. Now the fact that they are all orthogonal also tells us that S is a basis for R3. Now we have a theorem that basically says that later. But if you think about this, we've got 3 vectors, each at a 90-degree angle. That means they're all linearly independent and therefore will form a basis for R3 based on what we know about bases and orthogonal vectors. Now we have to determine if each of these is in fact a unit vector. So again, we're just going to find the length of each vector, Radical 2 over 2 squared, so that's 2/4 or 1/2, 1/2, 0. So V1 is 1, V2 is 1, V3 is 1. Therefore, we know that V1, V2, V3 is an orthonormal basis. Now your textbook takes you through another orthonormal basis for the Fourier series in calculus. I decided instead I would let you look at that one on your own, and I would take you through the orthonormal basis for P3, which is the polynomial of degree 3. So again, if we're trying to find that this is an orthonormal basis, we're going to follow the same steps. We're going to determine if each pair is orthogonal. Once we do that, we determine if each vector is a unit vector. Now, the hardest part of this one is really understanding what each of these ordered quadruples would look like. So if I'm looking at 1, that is really 1A0 plus 0A1, 0A2, 0A3, because this is 1 plus 0x plus 0x squared plus 0x cubed. And x would be 0 plus 1x1 plus 0x2 plus 0x3. So that would be 0, 1, 0, 0. So once you get that, then it's super duper easy. Are they orthogonal? Yes. Each pair, so again, there were 6 pair this time. Each pair is orthogonal. Are they all unit vectors? Yes, they're all unit vectors. Therefore, the basis, the standard basis, is in fact an orthonormal basis. Here's a few handy theorems that we now can use dealing with orthogonal or orthonormal sets. First, if S is an orthogonal set of non-zero vectors in an inner product space, then S is linearly independent. So we talked about the fact that yes, it would be a basis. It can only be a basis if it's linearly independent and spans the vector space. Additionally, if V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors is a basis for V. So again, we were dealing with R3 a few moments ago, and I said, well, that also shows it's a basis. This is what I'm referring to. So we had dimension 3. Any orthogonal set of 3 non-zero vectors is a basis for that, in this case, R3. If the basis is an orthonormal basis for an inner product space, then the coordinate representation of a vector W relative to B is taking that dot product or inner product of W, which with each of the vectors, multiplied by the vector. And this just relates to that. So this is saying if you want to find the corresponding coordinate matrix of W relative to B, so again, this is just a change of basis, then we're just trying to find those C values, those scalar values, and to find the scalar values, we're just taking W multiplied by each of the original vectors in the vector space. So we're going to use this in our next example. So we have a coordinate matrix of W, 5, negative 5, 2. So W is what we're working with. And we have an orthonormal, obviously non-standard basis B. So standard basis would be 1, 0, 0, 0, 1, 0, 0, 0, 1. This is a non-standard basis. What we want to do is essentially a change of basis. Now we're told that B is an orthonormal basis. So we don't have to check that this is orthonormal. They're telling us it's orthonormal, so we don't have to check if all of the vectors are unit vectors. We don't have to check if they're orthogonal. We can assume that to be true. Now we can use this formula to then find the coordinate matrix of W relative to the orthonormal basis. So how are we going to do that? We're going to take WV1. What we mean by that is W is 5, negative 5, 2. and I'm finding the dot product with V1, which is 3/5, 4/5, 0. So again, 5 times 3/5 is 3, negative 5 times 4/5 is negative 4, 2 times 0 is 0. So we're just finding the dot product of this. 3 plus negative 4 plus 0 is negative 1. And so that is WV1. And as you can see, I'm going to do the same for WV2, WV3. So for WV2, same idea. We're just doing the dot product. Negative 7 is my solution. And for WV3, I get 0 plus 0 plus 2, or 2. So what that tells me is if I did a change of basis, I would use 5, negative 5, 2 would be rewritten as negative 1, negative 7, 2. So that would be the coordinate matrix of W relative to the orthonormal non-standard basis. Gram-Schmidt orthonormalization process. The Gram-Schmidt orthonormalization process is simply a method in which we can find an orthonormal basis given any basis. So we're going to begin with a basis that doesn't need to be orthogonal and it doesn't need to be unit vectors. They're just going to say, here's a basis. Then we're going to convert the basis to an orthogonal basis. So again, that's using a change of basis. So we're going to convert the basis to an orthogonal basis, and this is the method that we're going to follow to do that. And we can see what the pattern is here. So for V1, it's just the same as W1. So W1 is going to be whatever our first vector is. So that's the vector we choose. Our next vector, we're going to take vector 2, and then we're going to find the inner product of V2 with W1, and then W1 with itself, and multiply it by W1, and we're going to subtract that from V2. And then for the next one, notice we have V3 W1, 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 and then V3 W2. So we're going to be subtracting 2 products. And then if we went to W4, we would do the same. So it's just a pattern. Then you can normalize each vector in the orthogonal basis to form an orthonormal basis. So again, we're just going to find each as a unit vector. Now, I'm going to show you this method, and then I'm going to show you when we do these in the opposite order, which may make the calculations a little bit simpler. It's really kind of up to you which one you like better. But when we get to the end, B double prime, this is actually B prime. We're converting it to a new basis, and then we're making it a unit basis, so that's B double prime is an orthonormal basis for V. Let's take a look at an example. So I want you to try to focus on just what we're talking about at the time that we're talking about it. I didn't want to uncover anything as we went, just to make it clear so you don't have to worry about trying to copy anything down. So here's what we're doing. We are using W1 is equal to V1 first. So here is V1, V2, V3. So the first one's very easy. W1 is exactly the same as V1. So W1 is 1, 1, 0. Now, W2, it says take V2, so V2 is 1, 2, 0, and subtract, and now we're going to use W1 here, but then this is V2 W1, so that's V2 1, 2, 0 dot product with W1, which is 1, 1, 0. So we get 1 times 1 or 1, 2 times 1 or 2, and 0 times 0 or 0. That's where those numerator values came from. The denominator values came from 1 squared plus 1 squared plus 0 squared. So that gives me the 1, 2, 0 minus, and then I just simplified. This was 3 halves, so 3 halves times 1 is 3 halves. 3 halves times 1 is 3 halves. 3 halves times 0 is 0. And so W2 is negative 1 half, 1 half, 0. So we have W1 is, let me take this in blue. 1, 1, 0. W2 is negative 1/2, 1/2, 0. And then W3, again, I'm going to just follow the formula. And the formula says take V3, so that's 0, 1, 2, 0, 1, 2. And then I'm going to subtract V3.V1. So now I'm not using V2, I'm using V3.V1. So 0, 1, 2, dot product. That gives me 0 plus 1 plus 0. That's my numerator. Denominator, 1 plus 1 plus 0. And I'm multiplying it by W1. And then I'm doing the same thing using V3W2. So V3W2 means 0, 1, 2, and negative 1/2, 1/2, 0. So 0 times negative 1/2 is 0, 1 times 1/2 is 1/2, 2 times 0 is 0. That's where this numerator came from. And then dot product with itself, 1/4 plus 1/4 plus 0. And then again, I'm just doing some simplification. So the hardest thing here is you're doing a lot with fractions, and it can get a little bit crazy, especially with radicals and fractions and so forth. So we can see that when I do the math, that gives me that B prime is 1, 1, 0, negative 1/2, 1/2, 0, and 0, 0, 2. That is an orthogonal basis, not orthonormal, but orthogonal. Now to make it orthonormal, all we have to do is take each of those vectors and then apply the unit vector formula, which says find the length of the vector and divide by that length. So here, again, I'm taking 1, 1, 0, which is that first vector, and I'm taking 1 squared plus 1 squared plus 0 squared, so I'm taking each of those divided by the square root of 2. So that gives me the first vector, U1. Do the same thing for U2, and the same thing for U3. So B double prime, which is our orthonormal basis, is now radical 2 over 2, radical 2 over 2, 0. And then negative radical 2 over 2, radical 2 over 2, 0, and 0, 0, 1. So this is an orthonormal basis. Now, instead of going in that order where we find all of the orthogonal basis first and then normalize it, which means make them all into unit vectors, you can also go in an opposite order. You'll notice it's 6 in one, half dozen in another. You're still going to do a lot of math, but there might not be as many confusing parts. And again, that's to say, go ahead and find U1 first, which is V1 divided by the length. And then you get to use that moving forward. So instead of using V1 and then at the end normalizing it, you're basically normalizing it as you go. So I normalized it to go ahead and get my first vector, which as you'll notice matches the first vector that I had before. And then I'm going to find U2, but U2 is found using W2 is V2 times the inner product of V2 U1. So it's really the same thing. It's just the order in which you are normalizing it changes. So here, notice I'm normalizing here and then using that normalized vector in W3. So notice I am getting the exact same solutions that I got before. It's really up to you which method you prefer. We're going to go through one more example, and I'm going to ask you to use the alternative form, or I'm going to use the alternative form. You can use either form, and then we'll just check our work together. This is our last example, but this one is a little more involved than the last question. In the last question, we were given the basis. Here, we're given a homogeneous linear system, and we are trying to find the orthonormal basis for the solution space. So really what we're doing is taking something we already know how to do, which is to find a solution space for a homogeneous linear system. And then we're going to take that solution space and then find the orthonormal basis for that. So I would like you to do this first part, which is really solve the system, find the basis for the solution space. Hopefully we know how to do that. We've been doing that a lot. So press pause, try that part of the question on your own. When you're ready, press play to see how you did. So first thing I'm going to do is put those values into a matrix. 1x1 plus 1x2 plus 0x3 plus 7x4 equals 0. 2x1 plus 1x2 plus 2x3 plus 6x4 is equal to 0 is represented right here in this matrix. I do some math magic to determine what is this in reduced row echelon form. Once I get into reduced row echelon form, I know that this translates into x1 plus 2x3 minus x4 equals 0, which I would rewrite as x1 is equal to negative 2x3 plus x4. And then x2 minus 2x3 plus 8x4 is equal to 0, which I would rewrite as x2 is equal to 2x3 minus 8x4. I'm going to let s be x3. So think about just taking s for s3 and t for x4. And that gives me this solution, which I've written parametrically, which means the basis, not the orthonormal basis, but the basis for this solution set is negative 2, 2, 1, 0. 1, negative 8, 0, 1. Now we have our basis for our solution set. Now we're going to apply what we've just learned using the Gram-Schmidt orthonormalization process. So again, I used the alternative form where I said, let's let U1 be V1. So U1 is this first vector. And then I'm just going to go ahead and make it a unit vector. So I'm going to divide by the norm, or the length of that vector. So the square root of 4 plus 4 plus 1. So 2 squared plus 2 squared plus 1, which gives me the square root of 9, or 3. So notice I've just taken each of those initial values and divided them by 3. And that's U1. That's the same vector we had before. I just made it a unit vector. The second one requires me to do some work. So I'm going to just go ahead and find W2, which is V2 minus the dot product of V2 U1 times U1. So here's V2, 1, negative 8, 0, 1 from right here. I'm going to take U1, which is what I just determined, times V2. So I'm taking that times 1, negative 8, 0, 1 dot product. And that gives me negative 2/3, negative 16/3 plus 0 plus 0, which gives me negative 18/3, which is negative 6. So really I'm taking this guy times negative 6, and then I'm adding that to 1, negative 8, 0, 1. And that gives me 3, negative 4, 2, 1. That is not a unit vector. That is the orthogonal vector. So that's at a 90-degree angle. And then I'm going to go ahead and box this one in blue because this is one of the solutions. And then I'm just taking this and normalizing it, which means I'm going to make it a unit vector or divide by the length of that vector. So negative 3 squared is 9, negative 4 squared is 16, 2 squared is 4, 1 squared is 1. I get radical 30. So I'm taking each of those values divided by radical 30. And so my basis, my orthonormal basis, includes negative 2/3, 2/3, 1/3, 0, and negative 3 radical 30, negative 4 divided by radical 30, 2 divided by radical 30, and 1 divided by radical 30. These are two orthogonal unit vectors, or an orthonormal basis. Up next, mathematical models and least squares analysis.